right, so for the rest of this week, okay, we are going to be talking about different types of reactions and solution stoichiometry. So this is all going to be variations on a theme, okay? We are going to be revisiting, again, what you did in lab with the net ionic equations experiment. So the periodic table I gave you guys, and again, I've got extra ones up here. Okay. On the back of it, okay, it has lots of extra information. Okay. The main thing being the solubility table, okay, and some examples of strong and weak acids and bases, gas fluorine reactions, how to write reactions in solution. Okay, and so we're going to be this is going to be our main reference sheet for much of what we do having to deal with Chapter 9, okay? So let's get into it, okay? So we're first going to talk about types of chemical reactions. So you'll notice that there's a lot of terms in this chapter. Some of them are ones that you have, encountered before. You've encountered almost all of them in lab. And so here we go. All right. So as we go through talking about we're going to talk about types of chemical reactions, like what kinds of things can happen when we mix molecules together. Okay. So the first is a sort of, the name kind of tells you what it is, right? So these are called combination reactions, where you have two or more reactants, and they're going to form a single product, okay? So if we can look at the examples on the slide here, we've got hydrogen and oxygen gas reacting to form water, okay? So we have two separate things reacting to form one compound, okay? We've got SO2 and oxygen gas reacting to form SO3, okay? This happens, okay, in the atmosphere, okay? So when we burn fossil fuels and those carbon sources that we burn for energy, they have sulfur in them. Okay, burning is a chemical reaction where you're adding oxygen to the thing you're burning. Okay, so the hydrocarbon fuel will have oxygen, added to it. It will become oxidized, but so will any sulfur that's in there. Okay, and so what we get is this being, well, when we burn fossil fuels, this gets pumped up into the atmosphere as a gas. And when it goes up into the atmosphere, it encounters water droplets, okay? And what happens is that makes acid rain, okay? So it makes, this is sulfuric acid. Okay, so these two reactions up here, okay, are combination reactions, okay? And so is this one, okay? We're making one thing out of two, okay? All right, so most reactions that you have between just two elements, okay, are going to be a combination reaction, okay? So most reactions between two pure elements are of this type, okay? And these are, despite the fact that it's H2 and O2, those are pure elements. They only have one type of atom in them, right? So it doesn't matter whether they, exist as a diatomic molecule or whether it is a, single oxygen atom by itself. It's a pure compound. So another example of this would be we can have a reaction between mercury and oxygen, okay? And we can make that compound up there, okay? So that's, feature number one, okay? You're typically, when you have two pure elements, you're going to have a combination reaction, okay? The other thing, okay, is if we look at the periodic table, okay, and we're thinking about reactivity, okay, and elements, right? If we look at the halogens, they're group 7. They're so close to being noble gas electron configurations, okay? And that makes them very reactive, okay? So halogens are very reactive, and they tend to participate in combination reactions. So halogens, and that's group 7A. So they're very reactive elements. And participate in oxidation reactions. Oops, nope, combination reactions. Okay, so the other element, okay, that is highly reactive and participates in a lot of combination reactions is oxygen, okay? It's right next to fluorine on the periodic table. It's highly electronegative. It's highly reactive. So it participates in many combination reactions. Okay. All right. So we can combine elements or molecules to make a new chemical. Okay. We can also take a chemical and break it apart. Okay. And this is what's called decomposition. So this is when we have a single reactant breaking up to form two or more products. Okay. So you'll notice that there's a reaction that you've seen before in the opposite direction here. So if the formation of water from oxygen and hydrogen is a combination reaction, okay, then if we take water and we break it up into hydrogen and oxygen gas, and you can do this with electricity, okay, so if you are if you're someone who has ever been in a biology lab where you've done agarose gel electrophoresis, where you take DNA and you're using an electric current to make it move through a gel, okay, if you look very closely at the apparatus that you're using, okay, it's got wires in it, and when you turn the current on, you'll see little bubbles coming off of the wires. That's actually hydrolysis of water that's happening at your electrodes. So the little bubbles are bubbles of hydrogen and oxygen gas as the electric current causes the decomposition of water. Okay. All right. So this is really, decomposition is really the opposite of combination reactions. Okay, and then, so here's one where we're taking calcium carbonate and we're breaking it up into calcium oxide and carbon dioxide, okay? Now, if you see, okay, something like a little delta sign over the arrow in your reaction, okay, what that means is I make this reaction go by adding heat, okay? So you can think of it as, a little flame, okay? So this symbol over a reaction arrow indicates heat, okay? So just like the decomposition of water, I have to add electricity in to break that molecule apart. Calcium carbonate is a stable chemical, at room temperature, but we can cause the decomposition to happen by heating it up. Okay. Water decomposition requires energy, okay, usually electricity. And we call this process electrolysis, okay? In chemistry, when we use the term lysis, okay, that means to break something, okay? This is used a lot in biochemistry, right? Enzymes are responsible for catalysis, often that means breaking things up, okay? And the electro just means electricity. So this is to break something with electricity. Okay. All right. Okay, so we can smack two things together and make a new one thing, or we can take one thing and we can break it apart, right? But what happens when things are a little more complicated and it's more like we have chemical entities swapping partners, okay? This is what happened every time you saw a precipitation reaction, or when you saw the gas forming reaction in the net ionic equations lab, when you saw a solution turn cloudy, okay, that was a precipitate, okay, and that was an indication, okay, that the aqueous things you started with, the fully solvated things, had a chemical reaction that occurred where the ions swapped partners and made a product that was no longer soluble, okay? So precipitation reactions are kind of a subset of displacement reactions, okay? These are also much more common than combination or decomposition reactions. So they're very common things. When we call it single displacement, what we mean is there is one part of our starting material that gets replaced by another one, okay? So one part, so here, the part that gets replaced is the A in the chemical AB gets replaced by the X, okay? And so now this is the new partner for element B in this case. And this is just generalized. This is not referring to any particular elements. We use A and B to mean, element A, an element, another element, and then X is a third element, okay? So what this looks like, okay, so most of these reactions, okay, involve metals. Involve metals. So if we look at this, okay, so we've got copper chloride. Okay, so in this case, okay, the copper is the A, okay, and the chloride is the B, right? And then the magnesium, okay, is the X, okay? And so the magnesium is going to take the place of the copper. And now you have magnesium chloride, okay, as your product, and then copper just on its own, okay? All right, so if we go back, okay, to when you did the periodic properties lab, and we had the pieces of sodium and potassium metal in the hood, okay? Do you remember taking the piece of litmus paper, okay, that would tell you whether the solution was acidic or basic, and you dipped it into the solution after the water reacted with the sodium, okay? That you were actually, okay, testing this reaction right here, okay? So this is a reaction of sodium metal with water, okay? And it turns out, okay, that this is a single displacement reaction, okay? So if I write this not as H2O, but if I write it as HOH, and sodium, it might be easier to see how the displacement occurs, right? So I have the sodium replacing one of the hydrogens, okay? And so that's how I get my sodium hydroxide, okay? And then this hydrogen combines with, a second hydrogen that gets lost from a second water molecule and makes the hydrogen gas, okay? Now, sodium hydroxide, okay, is a strong base, which means that when it's in water, it breaks up into sodium ions and hydroxide ions, okay? And this is the thing that turns the litmus blue, or purple it was, okay? All right, so you did a single displacement reaction in lab. Okay, you did the reaction of sodium with water. You also did, okay, a lot of double displacement reactions, okay? And we're going to get, in the next slide, we're going to get into precipitation, okay? So double displacement reactions, these are probably the most important of the types of reactions that we're talking about, okay? They're also called metathesis reactions. I don't like to use this term. I prefer double displacement because it's just tells you what you're doing, right? You're like two things are being swapped, okay? And what that means is instead of having a single element alone all by itself, okay, swapping for an element in another compound, okay, you have two binary compounds that have, two elements or an element in a polyatomic ion, and it's more like, in square dancing when you have two pairs and they swap partners, okay? So most of the time, okay, it's ions that are exchanging, okay? So again, here you've got this element replacing the X and the X replacing the A, okay? So where have we seen this before? Again, in our precipitation reactions, okay? So here's a reaction where when you mix two chemicals, you get a double displacement reaction happening, and one of the products is insoluble. So you get double displacement reaction, where one product is not soluble. It means it does not dissolve in water, okay? So the word we use for not soluble or not dissolving is insoluble, okay? All right, so when we look at precipitation reactions, okay, we break kind of the reactants and products up into what things are floating around in solution. When you put an ionic compound in water, okay, the attraction of the polar water molecule for the charged ions, okay, causes them to break apart and be surrounded by water molecules. That's what it means to dissolve. So I'm just going to draw a silly little picture of our lead nitrate dissolving. Okay, so there's my lead ion. Can somebody tell me what the charge on the lead is going to be? You can do it based on the formula, and if you remember, what nitrate? Yes, +2, because nitrate is NO3 minus, right? So when this thing breaks up into water, okay, I'm going to draw water molecules as little blue balls. So when this thing goes into solution, which is what this aqueous means, Okay, what it means is that my ions break apart from one another and they are surrounded by water molecules. Okay, that's what it means to be soluble. Okay, it means that the thing that goes into solution is surrounded by water. Now, if I have a molecular compound, something that's not ionic, a covalent compound, okay, they can dissolve in water too. Okay, so if you take sugar, the sugar molecules are going to stay intact, okay, but they're going to become surrounded by water too. Okay, so this is dissolution of an ionic compound. And just for reference, a covalent compound, excuse me, I'm going to take I'm going to just draw a sugar molecule like this. And it doesn't matter what sugar this is. Let's see. All right, when I take that and I put it into water, okay, it's going to stay the same. It's not going to break up. Its chemical structure is going to look the same. But it's going to be surrounded by water molecules instead of packed against other sugar molecules, okay? All right, so when we talk about precipitation reactions, we figure out what we have in solution. So in this case, we've got our potassium ions, okay, and our sulfate ion. All right, and again, we're going to swap partners, and the sulfate is going to combine with the lead, okay, and then the potassium will combine with the nitrate. And one of those compounds, okay, in this case is going to be soluble. It's going to remain in solution. So that means that the potassium and the nitrate ions stay looking like this. They stay surrounded by water molecules, okay? And then the lead sulfate, okay, because we have the solid there, okay, that is insoluble, and it forms what we call a precipitate. And we say it precipitates out of solution. So what that means is that instead of individual lead ions being surrounded by water molecules and individual sulfate ions being surrounded by water molecules, what you get is you have a bunch of these guys packed against one another, trying to avoid the water at all costs. Okay? And in a little bit, okay, we will, when we talk about writing net ionic equations, we'll talk about using the solubility table, which you've already used before, okay, to figure out if something's going to precipitate or not. Okay, so the other type of double displacement reaction that's super important, okay, is something that you used in lab last week, okay, when you did the titration, okay. So acid-base neutralization reactions, okay. And so when you have two atoms, okay, or ions that exchange, do this double displacement thing, okay, and the chemicals that you're dealing with are an acid and a base, okay. So our definition of acids, okay, is a hydrogen ion donor. Okay, we call them proton donors because that's what a hydrogen ion is. And a base accepts a proton. Okay, this is what we call the Bronsted-Lowry theory of acid and bases. There is another theory called Lewis acid-base theory, where we consider an acid and a base as electron pair donors or receptors instead of hydrogen ions. So instead of looking at the perspective of, the positively charged thing being added onto a molecule or being lost from a molecule, you are looking from the perspective of the molecule that's accepting the proton, which if it's making a bond to that proton, that molecule is donating both of the electrons, okay? And the reason that we use Lewis acid-base theory as opposed to Bronsted-Lowry, which is this one, is there are some molecules, okay, that it expands the range of molecules that can have the behavior that we consider as being characteristic of an acid or a base, okay? All right, so let's look at what an acid-base neutralization reaction looks like. So in this case, okay, one of the partners that swaps, okay, is going to be a proton, okay? So we've got our potassium ion, okay, and we've got our hydrogen ions, okay, and so they're going to swap partners, okay. What happens when you add a hydroxide ion plus a proton, okay? Well, you get water, okay? So when you have a reaction between an acid and a base, okay, water is always a product, okay? Water is always product in an acid-base neutralization reaction. So why do we call it neutralization? Okay, so, all right, so our hydroxide, and the sulfate also swap, okay? So the reason we call it neutralization, okay, is because when we call something an acid, okay, it's what we call a phenomenological definition, okay? What that means, okay, is we define acids based on sort of the chemical reactivity properties of the compound, of the material, okay? And so things that are acids are all going to have some type of reactivity in common, okay? And in the case, again, of Bronsted-Lowry acids, that is giving up a proton, okay? So in terms of something you can experience, okay, acids, okay, are chemicals that taste sour to us, okay? So acetic acid, which is the acid in vinegar, okay, has a sour taste. Ascorbic acid, which is vitamin C, and the acids, citric acid, which is the white powder that they put on sour candies. Okay, all of those things taste sour to us, and that's because on our tongues, in the area where we have the sour taste receptors, okay, there are molecules that bind to protons. Okay, and protons, okay, when they bind to this receptor, send a signal to our brain that we interpret as sour, okay? Now, if you take an acid and you mix it with something that's basic, so let's say you take your orange juice and you put a little baking soda in it, okay? The sourness is going to go away because the protons, okay, have reacted with the base and, again, form some water molecules, okay? And that doesn't taste sour to us because we don't have free protons going around in solution, okay? So when we call something a neutralization reaction, what we mean, okay, is that we've neutralized, and to neutralize something is to kind of stop it, right? And so if you're neutralizing an acid, you have a reaction that makes the acid kind of go away, okay, so that it doesn't react like an acid does anymore, okay? All right. So the other type of reaction that you saw that was in the net ionic equations lab, which was a double displacement reaction, okay, is what we call a gas forming reaction. And this is really, you have a double displacement reaction that has a secondary reaction that happens afterwards. So this is a secondary reaction happening after the double displacement. Okay? And that secondary reaction has gas as a product. As a product. And how do we know this? We see bubbles, right? So the first reaction is the double displacement. The second reaction, okay, is where the product of your first reaction is unstable and it forms a gas. Okay, so this product right here, okay, is the product of our double displacement. Okay, and this is an unstable molecule. And it decomposes, okay, into water and carbon dioxide gas. So, spotting gas-forming reactions, okay, if you look, there's really 3 types of gas-forming reactions. So there's 3 unstable products that you can get, okay? And there are things that involve carbonates. So if you see, again, if your initial product is a hydrogen carbonate, okay, or if you have hydrogen sulfate, okay, or if you have hydrogen sulfide, oops. So these are all going to, well, this is the product of that. So let's, So those are the only 3 you have to worry about in terms of gas-forming reactions. Okay? So this is your double displacement. And this is your decomposition to gas, okay? And so when we write the overall reaction, okay, we combine these 2 processes, these 2 steps here, and we show what the actual products are. And the thing that disappears, okay, is the thing that decomposes, and it's not shown in the overall reaction, okay? So you're going to know that it's a gas-forming reaction because it's going to form a gas. And that gas, is either going to be, so the 3 gases you can get CO2, SO2, or H2S. So these are the 3 possible gases when you have gas-forming reactions. Okay, so double displacement reactions are pretty common in biochemistry, where you have where your purpose of many of your chemical reactions is to build molecules, break molecules apart, or change where chemical groups are on your molecule, okay? And so there's something called a ping pong enzyme mechanism, where you have 2 atoms or ions that are exchanging, okay? So, in this case here, you have two separate molecules, and they look very similar, right? But there is a distinct difference. So there's an extra carbon here, okay? So what you're doing, okay, and anytime you see like two lines coming together in one of these abbreviated structures, that's a carbon. Okay, so here we've got two carbons in the chain. Here there's only one carbon in the chain. Okay, so what we're doing in this reaction is we're moving this, what we call an amine group, onto here, and we're moving the carbonyl group, okay, onto the smaller molecule. Okay. All right. Okay, so what we're going to do is we're going to talk about aqueous solutions next time. And I'm going to, there's a case study example for precipitation reactions. So I'm going to record that part as a video. So we're going to go over the aqueous solutions. I'm going to skip the case study, and you guys can kind of view it outside of class as another example. And then we'll move on to the next class of reactions, okay? All right, have a good afternoon.